day. I am Dr. Addison, and in today's exciting feature presentation, we are going to look at sampling distributions. Here is a quick outline. We'll explore the concept of a sampling distribution, look at the central limit theorem and its attributes, explore real-life applications, and we will have pertinent references and readings in the field. Let's get started. By the end of this session, you'll be able to define important concepts related to sampling distributions, apply the central limit theorem in a practical scenario, and examine real-life applications of the central limit theorem, or CLT as it's usually called. So let's look at a quick recap of some of the concepts we used last week, which will enable us to understand today's lecture. Parameters versus statistics. We know that parameters describe populations, whereas statistics describe samples. Parameters give us fixed values for a given population, whereas statistics change from sample to sample. And parameters are usually unknown values in practice, whereas statistics are calculated for a given sample. So let's dive into sampling. We recall from our previous lecture that sampling itself is a very effective way to make inferences about a population. Statistical inference relies heavily on the concept of sampling distributions. So therefore, we would like to explore in today's lecture the what, how, and why of sampling distributions. We would look at defining the idea of the sampling distribution, use an example to showcase how to find the sampling distribution, and then discuss why it is used in relation to the central limit theorem. So let's first look at what a sampling distribution is. It is a probability distribution of a statistic, where all possible samples of the same size are derived from the same population. How then do we create a sampling distribution? Let's have a look at our previous example to showcase how we can derive a sampling distribution in the lecture today. We previously assumed that there's a population of size n equal to 4, where the measurement of interest is the age of individuals, with those values being 18, 20, 22, and 24 years old. In this example, we took samples of size n equal to 2, and we were able to recognize that there would be 16 sample means. If you need a recap, here it is. So you are able to draw samples of size n equal to 2, and it looks like the following. In the table, we can see all the observations of ages written in a coordinate format. So for instance, our first sample is made up of age 18 and age 18. Our second sample is made up of age 18 and age 20, and so on. This ensures that we have 16 possible samples, and we learned that this is sampling with replacement. Next, we can compute the sample means for each of these samples, as shown. We can see that the first sample mean of 18 corresponds to the average of the values 18 years and 18 years, and so on. The next sample mean is the average of the values 18 and 20, and so forth. Moving from our second step into our third step is fairly a straightforward process. We can now use these values to plot the distribution or histogram. And as you can see, when the values are plotted against the probabilities of each of the values occurring, we see that it has a symmetric shape if we trace a line around the bars. This observation is clear. The distribution is symmetric or somewhat normal in appearance. These are the three main steps used to create a sampling distribution. So why is this used? What is the bigger picture of the sampling distribution itself? Well, as we see, as a sample size gets large enough, the sampling distribution becomes almost normal regardless of the shape of the population, and that was clear in our previous example. What does this mean in a mathematical context then? We can derive the central limit theorem, which states that x1 to xn, which is a random sample from a distribution with mean mu and variance sigma squared, has a sample mean x bar, and this is approximately normally distributed with mean mu and variance sigma squared on n, once n is sufficiently large. In this case, the rule of thumb is n greater than 30. We must note that the larger the value of n, the better the approximation. So let's put this into practice. The following is a tutorial question from the tutorial sheet, which is lodged on My Learning, for your perusal. We will have a quick look at the methodology to solve this question. It reads as follows. Verify that there is a probability of 29.5% that a sample of 100 automobile insurance claim files will yield an average claim of 4,527.77 or less if the claim, or the average claim that is, for the population is 4,560 with standard deviation of 600. All of these are measured in currency. So the guided steps would be as follows. We first need to understand what is the goal of this question. What is it asking us to compute? We can see here that it's asking us to show that the probability that the sample mean x bar is less than 4,527.77 is equal to 0.295, which in essence is 29.5%. Here are some steps which will allow us to show this value. Now, since the question stated that n is 100, which we know by our previous rule of thumb is greater than 30, we can see that by the central limit theorem, the sample mean x bar is approximately normally distributed with mean 4,560 and variance 600 over 100. The next step would be to standardize. As we recall in our last computation in the previous lecture, we use z values according to the equation x bar minus mu divided by sigma on root n. If you need a refresher on this particular step, feel free to refer to the last tutorial with several worked examples and reach out to me if you need further assistance. Moving along, we use the standard normal tables for the probability z less than minus 0.54, which would have been the computation gained from step 2. This is a straightforward computation which we can gather from our normal distribution tables, which are also lodged on My Learning. In the fourth step, we can conclude that the probability is the original probability that we stated. Have no fear. If this seems to be complicated in any way, feel free to look at the full solution for this question and use the tutorial sheet to practice other questions in this topic. They are all available on My Learning. Moving right along, we want to think about what are the real-life uses of the central limit theorem. Here are some for you to research further. Now, the central limit theorem is very useful in confidence interval analyses and hypothesis testing. We see it come into play in surveys in terms of the number of the sample size taken, also in economic applications, biological procedures, and agriculture. An amazing opportunity to research this further in terms of data science applications comes from Bruce and Bruce in 2017, a paper which discusses that bootstrapping is a useful alternative to confidence intervals and the use of the central limit theorem. Feel free to refer to this reading on My Learning. So after this exciting discussion, what are the overall takeaways? Well, we learned the what, how, and why of sampling distributions. We learned that a sampling distribution is a probability distribution of a statistic, example the sample mean. We learned how to obtain it through repeated sampling of the statistic from a specific population. And we also learned why it's used to draw conclusions about the population mean using the central limit theorem. So what's next? In the next lecture, we will actually use these tools and principles to find sample statistics and use these to estimate population parameters in what we call point estimation. We will also explore the construction of intervals to estimate where these population parameters may actually fall. And this is referred to as confidence intervals. So here are some quick references and readings for your review. Please ensure that you go into the J. Devoir text, which is the recommended text for this course, and the required reading is shown. Also note that you can continue the conversation in the My Learning Sampling Distribution Forum. Also feel free to contact me with any questions or concerns you may have. Thank you for your attention.